Method evaluation and validation. Student t-test. So student t-test is a statistical test that takes two sets of data and compares them to see if they're pretty similar or if they're really different. So it'll look at the average and it'll look at the variances that were created between two different samples or two different series of test results. So as an example, if we were to bring in a new analyzer and we're trying to see if this new analyzer is able to successfully report patient results just like our existing analyzer, what we could do is run a t-test. And this is useful to determine whether there is a statistical difference or bias between the two methods. It can't determine the cause of the difference, but it can say, yes, there's a difference and we have a problem. Bias can either be positive, where like the new analyzer or the new method's results are higher than the reference method, or negative, if they're lower than the reference method. It can be an indicator of the accuracy of the new method. For most clinical laboratory applications, the formula for paired t-tests is used. So I'm going to show you a data sample. And here's analyzer 1. So patient 1 on analyzer 1 tested as being 5. Patient 1 on analyzer 2 tested at being 7. So right now we can see that analyzer 2 is testing a bit high. And we can go through all of these values one by one and kind of look at them. But if you have hundreds of values, you need a quick statistical test to be able to perform this for you. And that test is the t-test. So in Excel, when you open up an Excel sheet, you can go to Data and then Data Analysis over here. And Data Analysis has a bunch of different options. We already did descriptive statistics in the past. But what we're going to look at now is the t-test, paired two samples for the means. We're going to say OK. And for whatever reason, it's taken a little while to load this box here. So hopefully it pops up in a couple seconds. There we go. So what we're going to do here is for the variable 1 range, we're going to highlight the data that we have for variable 1. And for variable 2, we're going to highlight this data. And now we've got the correct data ranges that are in there. We always have the alpha set to 0.05 because we want that within two standard deviations away gives us 95% of the results. So we want that set at that level. So then I'm just going to press OK. And here is what pops up. So what we're looking at now is in the first set, our average was 5.5. In the second set, our average was 8.7. We can already start to see a difference. Variance was calculated to be 0.967. That's pretty good variance. And when we look at the other data set, we see 53. That's a really high variance. So very all over the place type data. And then there's the number of observations. So there were 18 paired data samples. And when compared, we go down to like all of this could be explained in a statistics class, but this is not a statistics class, so we're going to kind of keep it just what is the bottom line here. If we go down here, one tail is looking for a difference in a very specific direction. Either you are intentionally looking for it to be too high or intentionally looking for it to be too low. Typically, we look at two-tailed. We want to see if there's a bias being high or low. And here we have 0.08. So this is our p-value for a two-tailed test. This is the value that we care about. What we would like to see is it less than 0.05. And in really good data sets, when we're talking about data sets that are very closely matched, where the first analyzer said the patient was 5 and the second analyzer said it was 5. The first analyzer said it was 6, the second one said it was 6, where they're very closely aligned, we want to see a p-value of just 0.00000000. Now with a p-value of 0.08, that means it's above the cutoff range of 0.05, which means there's a problem with the second data set. So our new analyzer that's coming in has an issue. Now, we can say that because we're testing this new analyzer against a previously used method. If you have two new analyzers, you can't say that one or the other is the problem because there's no way to tell which analyzer is the problem. All this tells you is that, yes, there's a difference between the values that are being reported out on these data sets. So if you have two new analyzers, then you're kind of wondering which one is the problem. And you can kind of go manually look through the data and get some results that way. But in practice, when we had an analyzer that is tried and true and QC'd and maintenanced and maintained and given us all sorts of good data for years, and now we bring in a new guy, we can kind of safely assume that the new analyzer being brought in is the one that's the issue, and that's what's creating this p-value of greater than 0.05. And 0.05 is always going to be our cutoff for this statistical test. So then going back here, we're going to continue on with our slides. New methods are generally proposed for improved lab service, expanding the tests offered, decreasing of turnaround times, improving precision and accuracy, reducing overall costs, upgrading to an automated method, and new technology. But there's several factors to consider. Is there a sufficient need based on the number of potential patients for the test to be analyzed in-house? What are the intended goals for this test? Screening, confirmation, diagnosis? What degree of precision, accuracy, sensitivity, and specificity are required? What is the medical decision limit? What methods should be selected? Do you have space for the new instrumentation and reagents? And can you handle the increased workload? Once you determine that you're going to bring a new test in-house, you must perform a method validation to include a patient comparison study. So this is a correlation of the new method with a comparison method. Comparison method may be a reference method or currently used method. So you, in the example I gave, you could be comparing it against the analyzer that you currently have, or you could be comparing it against a reference method. Differences are interpreted as systemic analytical errors. You determine the sensitivity, specificity, positive predictive value, and negative predictive value of the test. Testing precision, estimation of the random analytical error of the method. The mean, standard deviation, and percent CV are calculated from the data collected, and QC values are established. The observed SD is compared to allowable SD. If the SD and percent CV exceed expectations, then validation studies should be suspended until precision is improved. Determine the reportable range. The linearity, the range of the specimen concentration over which method may be used without dilution, also called the analytical measurement range, should match what the manufacturer tells you. Also, check the minimum detection limit, the smallest single result that can be distinguished from zero. Interference studies. Check for constant error and include common interference from hemoglobin, lipids, bilirubin, drugs, and anticoagulants. And the recovery studies involve adding a known volume of standard solution to a known volume of patient sample in a tube, and in a second tube, adding the same volume of diluent to the sample volume. The difference is expressed as a percentage. Estimates proportional systemic error. Accuracy is further measured by comparison of the test result to the gold standard method for which accuracy has already been established. Linear regression analysis, comparison of two methods, should form a straight line if the correlation is good. Random error is shown at points that are away from the curve. Correlation coefficient, 0 is no relationship, 1 is perfect, -1 is an inverse relationship. So now you can see the difference between a strong correlation and a weak correlation. So strong means all the data points are right along that central line. Weak means that the data points are kind of scattered all over the place. There's other graphs like a difference plot and a Uden plot. We won't talk too much about those, but again, we're trying to look for that linearity and see how far off these plots that data can land. Accuracy, the agreement between measurement and the true value. Studies are designed to detect systematic bias between two methods. You analyze 20 to 30 samples that span the reportable range of the method on both the new test method and a reference method. Most laboratories today use computer programs specifically designed for the clinical laboratory to calculate results. Recovery experiment. So in a recovery experiment, an accuracy study designed to determine whether proportional systematic error exists in a method. So 20 to 30 samples with known values are split into two aliquots. In the first aliquot, it's a reference aliquot. The other one is spiked with a known amount of the value. The reference aliquot is spiked with the same volume used in the test aliquot, but with diluents. Total volumes of each aliquot are the same. So basically in one tube, we have normal patient stuff plus a known amount of added stuff. And in the other tube, we have normal patient stuff plus the same quantity of stuff that was added in the first tube, but what we're adding now is diluent. We're not actually adding any substance that's going to change the value. So the total volumes of each aliquot are the same, it's just what you put in them is different. So the first tube had some like 5 mg of hemoglobin added, and the second tube had 5 mg of water added. So the volume ends up being the same, but different things are added to the tubes. The test and reference aliquots are tested in triplicate, so 3 times, and the average result for each aliquot is used for statistical purposes. Then you do the spiked value minus the control value to give you the recovered concentration. The percent recovery is equal to the concentration recovered divided by the concentration added times 100%. The acceptable recovery is 95%. Anything less is not considered acceptable. So as an example, a recovery experiment was performed on a sodium assay. 20 paired samples had 5 milliequal equivalents per liter of sodium added to the 100 microliter test volume. 100 microliter of diluent was added to the paired reference samples. Paired samples were analyzed and results were obtained. Calculate the percent recovery. Here is the reference and the recovery. Percent recovery is reported. Although there are values less than 100%, the average percent recovery was 95%, so this would be acceptable. An interference study. Interference studies are looking at systemic error, performed to determine whether the addition of a known interferent will result in an inaccurate result. Common interferents are bilirubin, hemoglobin, and lipids. Others, common cancer drugs, contrast media, or anticoagulants. Samples are paired as in the percent recovery experiment. One aliquot is the test aliquot, and it receives interferent. The other one is the test aliquot, and it receives diluents. Samples are tested over the analytical range of the instrument that is being evaluated. So then you do the average of the test aliquot result minus the average of the reference aliquot to see the bias. The average bias is then compared with the amount of error that is allowable for the test. Determining precision. So precision, the ability of a method to produce the same value for replicate measurements of a test sample. Precision of a method can be determined by its standard deviation and coefficient of variation. CLIA mandates that precision studies be performed as part of the method validation process. Within run study will help determine if random error is present, and between run study will help determine if systematic error is present. Laboratory may use the F-test as a measurement of precision. F-test is kind of similar to the student's t-test. Reportable range or linearity of a method must be determined by the lab for each moderate to high complexity test system used, determined by analyzing low and high calibration materials or control materials. Also determined by evaluating known samples with abnormally high or abnormally low values. A minimum of 3 replicates of at least 5 concentrations across the reportable range should be analyzed. A best fit line can be drawn. The x-axis is the known value, the y is the average of the replicate values. If a patient if patient results are higher than the highest reportable range, must be diluted and reanalyzed, and may be reported out as higher than the value of the highest reportable range. Patient values that fall below the lowest reportable range value can be reported out as less than. Samples of all ages and genders that are analyzed in the laboratory must be included in the study. CLSI currently recommends greater than 120 samples from each group that is analyzed by the method. The laboratory must ensure that the samples tested represent the patient population. Samples are analyzed, then the mean and standard deviation are established. The new reference interval typically includes 95% of the results. Then proficiency testing, quality assurance tool to assess the accuracy and precision of the laboratory's methods and instrumentation. CLIA mandates use 3 times per year for moderate or high complexity testing. Proficiency samples must be analyzed in the same manner as patient samples, and results are sent to an agency. Criteria for acceptable results depend on the analyte. Some have a target value with a small variable range. Some may use the criteria of comparing each result with the peer group's results. And here is a sample formula that can be used for proficiency testing when comparing each result with the peer group's result.